Hello again. Welcome back as we continue talking about the second law of thermodynamics. Now, do you want to mention I'm labeling this lecture 23. If you're following along, one might wonder where's lecture 22? Lecture 22, just for my labeling system, I'm calling that equal to there's a chapter on exergy in the um, Changle and Bowles text, and you find a chapter about exergy in a lot of different thermodynamics texts, and I don't really feel like frankly wasting our time with that. I just don't normally do it. If I've got an abundance of time, I used to do it, and it's a very simple concept. I don't spend a lot of time with it. Um, anyway, all that to say, I've left a placeholder, so if I find myself with like half of an extra day and really not much else to do, we'll do that lecture. But and who knows, maybe if you've already watched, if I go back after the fact and I add lecture 22 to this playlist, and it's like, Steve, I just watched lecture 22. I went back and added it later because I had an abundance of time for some reason. Um, we're skipping lecture 22. It's very much an optional topic. And we at this point in a thermodynamics course, right? If you look at what we've covered, lecture 1 through 21, we've really focused on the first law, second law, and using those in conjunction with other laws, rules, equations, relationships to solve problems. And that is for a thermodynamics one class. We've met typically your learning outcomes for a standard engineering thermodynamics introductory course. So we've kind of hit this point in the semester where we've kind of done what we would typically need to do for your course to transfer just about anywhere. There are some topics that is typically expected that when time allows, we continue to do, and that's what we'll do. I'm basically going to do what I consider Unit 4. So that's basically after an exam 3, before the final. So this is material for my class. This shows up on the final, but it doesn't show up on the first 3 exams, but it's still important, good information. And this is just the way this particular text that we're using is structured. Other texts will do our topic that I'm going to talk about today, which is isentropic efficiency. Other texts will do isentropic efficiency a little bit earlier. This one waits until a little bit later to do it. For us in the 10th edition of Changle and Bowles, they've actually moved this to chapter 8 now. Older editions before the ninth edition and older of Changle and Bowles, they have this massive behemoth chapter 7, and this is basically the second half of that chapter 7. But in the modern versions, it's now chapter 8. So that's what we're going to start talking about is what we call isentropic efficiency. I'm borrowing some slides a colleague of mine made. Well, I made kind of the original, and he substituted the course for me a couple times during this topic. And I've taken what he kind of modified my slides and added to them. I'm shamelessly stealing them, reusing them. I'm giving him credit. Not going to mention his name because I don't have his permission to, but at any rate, you don't necessarily have to know all that. If you notice, these slides are a little bit different than what I normally put together. Yeah, I've had some collaboration with a colleague of mine. Okay. So we're going to use his stuff in addition to my stuff, and we're going to move forward. Isentropic efficiency being our focus today is a tool that we use to expand on what we can do with entropy. And so some information here about what is entropy, expanding on kind of what we talked about last time with the third law of thermodynamics. Entropy being this thermodynamic quantity. Each material is going to have different chaos within it, depending on the phase and the behavior of the molecules. If I add heat to a body at some known temperature, I can figure out how much entropy I've added or removed if I remove heat at a known temperature. Um, and then, of course, the entropy generated. I love the way he's phrased this here. Entropy generation is a measure of the quality of the energy transformation from state 1 to 2 of the substance. A perfect or ideal transformation is reversible. meaning it's not generated new entropy that we didn't have when we started. So again, when you generate entropy, it's either in the system or the surroundings or both, but it's somewhere. There's more entropy than when we started. That's because nothing is perfectly reversible. And we believe destroying entropy is impossible. Okay. But what we might want to do is we might want to figure out, well, if I've got some process from state one to state two, or some device that takes material and converts it to some other phase of that or state of that material, I might want to know how good is that device at doing such things. The isentropic efficiency is a tool that we can use to measure the deviation of an actual process we might have in front of us relative to a corresponding ideal process, comparing the two. Just like any other efficiency or performance, comparing something to something else of the exact same dimension, the exact same type of measurement, and comparing how one stacks up against the other. Now, your text loves, the Changle and Bowles text loves to pretend that every single efficiency can be expressed as an output over input. And most of the time that works. Here's kind of a case where it starts to fall apart just a little bit, especially if we talk about compressors. But we're going to talk about a turbine first. If we talk about turbines first, right? The isentropic efficiency for a turbine would be the actual turbine work divided by the isentropic turbine work. What does that mean? Let me switch cameras on you here. Let's go to the document camera and let's look and see what that means. And I'm going to stop sharing so you can see this full screen, okay? So isentropic efficiency for turbines eta sub t, t for turbines, eta for efficiency. And we said earlier that is the actual turbine work divided by the isentropic turbine work. Okay. Now, if I look at a turbine, we know we're going to have mass coming in. We know we're going to have mass going out of the expanded or wider end. And we know we're going to pull a work out or a power output, work out. We know we're going to pull work out of this thing. And so if we do a first law, you've got minus this power output plus m dot times h1 minus h2. Maybe there's a kinetic change. Maybe it's insignificant. If it's an ideal isentropic turbine, that means it's adiabatic and reversible. So it's adiabatic, so there's no heat transfer. Right? So that means that the little w work out, that being the power output per unit mass, is equal to H1 minus H2. So here we're saying I'm going to compare any actual turbine to any isentropic turbine. So I probably will want to compare per unit mass, because then it doesn't matter how big or small this turbine is, I'm comparing apples to apples. And so I can compare any size turbine to any other size turbine through this ratio. So what we can do is we can say, well, to compare the isentropic efficiency, I can take the enthalpy change for an actual turbine and compare it to the enthalpy change for an isentropic turbine. Now, why this specific ratio? Well, remember, I tried to stress to you, again, I'm not the huge fan or advocate of output over input that the Changle and Bowles text is. One of the few places I don't care for what the text does. Output over input doesn't always work. What does always work is for a true efficiency, what do you expect to be the smaller quantity divided by what do you expect to be the larger quantity? And we expect that an actual turbine that you or I might construct or stand in front of and actually operate is going to generate less work out than the isentropic turbine will. So the actual turbine is going to be the work provided by the actual turbine is going to be my numerator because I expect that to be small. The ideal isentropic turbine, it's going to generate more, so or at least I'm going to expect that's going to generate more. It's going to generate the maximum work output. So that's going to be my denominator. That's the larger quantity. So that's going to go in the denominator of my efficiency. So with all that in mind, you go back to share here. I apologize. Here we go. So with that in mind, and here we are, right? Now, I'm neglecting heat transfer of the actual turbine. I'm neglecting any potential change in kinetic energy. I'm just focused on the enthalpy change. Gives me a good approximation for this quantity. If we look at that graphically, if I'm comparing the actual turbine compared to the ideal isentropic turbine. So I'm going to start at the same H1, the same inlet conditions. So inlet pressure, inlet enthalpy gives me some inlet entropy. Notice the isentropic turbine goes straight down. No change in entropy. It's isentropic, isoentropic, meaning constant entropy. The actual turbine is going to actually generate a little bit of entropy. So it's going to come out here to an S2 value that's higher than S1. So the actual turbine is going to come out to a higher entropy because it's being generated. So notice to get to the same exit pressure, to experience the same pressure drop from the inlet to the outlet, notice that to meet that same line of constant pressure, when you generate a little bit of entropy, you end up out here at slightly less H2 for the actual turbine as compared to the H2 for the isentropic turbine, right? So notice that, and we'll just do it in a different color here. Notice that the isentropic turbine comes down here to a higher value to meet the exit pressure compared to the actual turbine. So notice that the difference to get down here, the work for the isentropic turbine is less than the work for the actual turbine to get to the same exit pressure. And that's what this ratio is showing us here. Okay? This is showing us that the work of the actual turbine is going to be less than the work of the isentropic turbine. Okay. Yeah, that's good enough. I don't know why I backed up. If we look at, for a compressor. So the isentropic efficiency for a compressor, and I write up here instead of output over input, think of it more in terms of ideal over actual. Again, a true efficiency needs to be what you expect to be the smaller quantity divided by what you expect to be the larger quantity. Well, remember we've said in chapter 7 that the reversible compressor, the ideal compressor, is the one that consumes the minimum amount of work. So the least amount of work, that means that's the smaller quantity. That means that's going to go on your numerator in your efficiency equation. So this is the quantity we expect to be smaller, the work consumed or the work input for the isentropic device, the reversible adiabatic device. The actual compressor is actually going to consume more work, so that becomes our denominator. But in both cases, we could draw the same, basically, remember, a compressor is kind of the reverse of a turbine. So I've got mass going in, mass going out, and then I would have work going in. And your first law kind of looks the same way. It ends up being the work in is equal to the enthalpy change. In this case, H2 minus H1, because the sign changes. But otherwise, it's roughly the same quantity that for both the isentropic and the actual turbine, or I'm sorry, the actual compressor, the main driver of the work going on, the work required in this case, is going to be the enthalpy change. And so that gives us a really good approximation. I can take the change in enthalpy for the isentropic compressor divided by the change in enthalpy for the actual compressor, and I will get that the comparison of those two quantities will give me the efficiency. And so we can kind of see the same type of diagram, or very similar, kind of the inverted form of the diagram that we just saw for the turbine. Notice to get from they both share a common inlet or a common inlet state. To get from that inlet state to the isentropic outlet state, we go straight up, we go vertically to reach this higher pressure, the exit pressure. Which does not require as much of an enthalpy change. You can see WS here does not require as much of an enthalpy change to get from here to here as it does to get up to the actual enthalpy for the actual compressor that's going to generate entropy, and therefore has to get out here a little bit further along the S-axis to reach the same common exit pressure. Okay. So we're going to come back to this one, or we'll start a new video there and work an example.